You know us, we're always down to business right away. Okay, 8.3, fluid transducers. So we've done fluid and thermal system models now. So we've done all of them, but we're going to do an example, a very extended example with fluid transducer in it. And that'll just give you a flavor for the types of fluid transducers that are, I guess, to come or available or that you can model using these techniques. So the one we'll do is a turbine in this example, but there are a bunch of different options. But first, let's talk about thermal systems. So although thermal systems often exchange energy with other energy domains, it is much more common to consider those systems that interact with thermal systems to be generating or sinking heat, often modeled as a dependent source, than to see a proper transducer. So a dependent source, we haven't talked about really. I mean, we talked about it in passing a couple times, but it's a source like any other source that provides energy from outside the system. But a dependent source doesn't do so in an arbitrary way. So a normal source can set its, say, pressure, if it's a pump. You can like externally set what the pressure is for a pressure source. But a dependent source is one that is set by some variable inside the system. So it's not arbitrary. So for instance, a heat interacting with another system might do so based on what the temperature is in the system. So that's like a very common variable that it would depend on. So it's going to dissipate heat depending on what the temperature is of that body. And that's the type of thing that we'll see. I mean, you can model relatively easily, like the heat sink sort of model where you've got fins that have some nice cooling effect to it. Those are going to, say, sink heat to the environment away from your system, and they do so based on what the temperature of those fins are. That's going to be a big aspect of it. So those would be dependent sources. We do have to keep in mind that those are very common. We do also occasionally run into a thermal system that has an exchange with another energy domain, and that is probably the most fun case that I can think of. I'm sure there are other cool ones, but the most fun case that I've ever done is a thermoelectric cooler. Are you guys familiar with this? So thermoelectric materials, if you run current in one direction, it creates a temperature gradient in that direction. So like one side will get hot, one side will get cold. So you can exchange thermal and electrical energy through these. And it's pretty cool. You can create a solid state, meaning there are no moving parts. You can create a solid state cooler, like a little conditioner of the temperature of something with that. And actually 2 years ago, I gave this class that project to design and build a thermoelectric cooler base. I just recommended the thermoelectric cooler, wasn't required, but based temperature controlled chamber so that I could control the temperature of what was it? It wasn't kombucha, it was kefir. Because it's this fermenting milk stuff, kind of like yogurt, but it sits on your counter for like a day. But the temperature, like the quality of what comes out, depends a lot on the temperature. And so the fermentation process, depending on time of year and what the temperature of your kitchen is, it varies. So I was like, oh, okay, make one with a thermoelectric cooler. And they did okay. I had to help them a lot with the model. I have a history of giving. Last year I gave this water catchment tank system. There were a lot of nonlinear aspects to it, so I had to help them with that part. So I have a history of giving a lot of projects that require my help. So I don't know. So we'll see. I'm not sure if I'm going to do this semester. I didn't put it on the syllabus this year, so we'll see. Because I ended up doing most of the project, which isn't really the point of the project. So I didn't think it was very effective in the past. Okay, but anyways, pretty fun stuff. Thermal systems. And I haven't published that, but I think I should publish that model because it's not out there, the one that I used for the thermoelectric cool. It's pretty fun. So anybody wants to write a paper on that model, let me know, because I don't have time. So somebody can write it with me, co-authors. So, okay, great. Fluid systems, on the other hand, very naturally interact with mechanical systems. For instance, piston cylinder mechanisms, propellers, turbines, and impellers, or backward turbines, are just a few energy transducing elements. So these are very common, and we'll run into them a lot as mechanical engineers, depending on what field you work in. These systems are often driven by motors, for example, a pump's impeller, or drive generators. So a dam's turbine would drive a generator. Therefore, it is common to require a fluid electromechanical dynamic model. So fluid and mechanical and electrical all in one dynamic model. And without further ado, we will do just that. So, dams, even small so-called micro dams, generate hydroelectric power by directing water through turbines which rotate, creating mechanical power, and drive electric generators, generating electric power. For large-scale dams, the flow rate is regulated such that the AC generator produces a nice 60 hertz. So that's kind of the ideal case, is you've got an AC motor, well, generator, right? It's kind of the same thing. And you drive it so that it rotates at the frequency that you want, and you get a nice power signal out at the frequency that you're looking for that. So that's how dams do it. But the micro hydro stuff is as more of a niche thing. It's kind of a new like energy harvesting thing that you'll see people do. People are starting up little companies around them. I don't really know what the market is. I think it's like remote farm type situations or preppers. The earlier class didn't know what preppers are. Do you guys know what preppers are?
Doomsday preppers?
Doomsday preppers. Yeah. You definitely have a brother-in-law or a cousin who's a prepper. I have at least one or two. So every holiday I get to learn more about it. So yeah, they're going to save us when the zombie apocalypse comes. So. Actually, I realized this. So I have two sisters, and now they're both married to preppers, both of them. So Christmas is entertaining. It's really fun. So both preppers, and they're like always telling me I have way too few guns. Need a lot more guns, apparently. Oh, really? Yeah. Oh, yeah. And then also lots of ammunition. Those are apparently the two most important things. So, I don't know. I'm just betting on not the apocalypse. I just don't want the apocalypse. So.
You don't need a gun. You're an engineer. You can.
That's right. I make a gun.
No, you can make
sticks. Just give me sticks, some rocks.
Yeah.
Be good to go. Yeah. There'll be lots of scrap metal around. It'll be good. Okay. So, anyways, we don't want to get too distracted about on preppers. It's like a whole thing. But they do like think about energy in an interesting way because they want to be able to harvest energy very easily from the environment in a way that isn't tied to a grid. So it's kind of creates some fun problems. So I think that the micro hydroelectric stuff, my take, I don't know. I think that the market is mostly for that sort of group of people. Could be wrong though. Anyways, it's a thing that happens. Great. I think it's illegal to do it, though, actually, technically. Yeah, I think it's illegal to harvest energy from waterways.
From anything.
It's illegal to
Even
collect
from
rainwater,
rainwater.
so I'm assuming so.
Yeah, I think you can collect rainwater in Washington, but not in all states.
It depends on where you're at in Washington.
Oh, really? Okay. Yeah. So that's funny. Last year I did the rain catchment tanks, possibly illegal apparently in Washington. And
It
then
just depends on where you're at.
micro hydro, okay. I mean, it seems like we got a lot of rain here.
Yeah,
Hey.
they don't make money, so.
Yeah. Yeah, that's true. Okay, so let's talk more about this. So, great. So a micro hydroelectric generator typically cannot expect well-regulated flow rates. So you're not going to just get like, you don't want to build up so much apparatus that you're going to regulate the flow yourself. So you got to expect that you're just going to kind of get a bunch of different speeds coming through. And sometimes they use a brushed DC generator, in part because you then don't need to have it go at a very specific speed, very specific frequency to generate the power. And also because DC power is something that you can store in a battery, for instance, or you can charge a battery with, that type of power. So that's a reason to do a DC generator. The brush replacement being, of course, the primary drawback, as we've discussed before. So assuming a micro hydroelectric dam can be set up in a manner similar to a large-scale dam, draw a linear graph model from the following schematic. So hydroelectric dam figure here, it's got a reservoir of water that creates a nice pressure head to the intake, where we've got this pressure head, and we'll call this the C1 head. So this reservoir is going to change height, right? So we could, if it was always going to be at the same height, we could say, oh, that's some given pressure source that's always constant. But since it's something that is going to change in height, like so every reservoir does change in height over the course of a year. I mean, if you go over Snoqualmie Pass, you see the nice, beautiful lake, and then by the end of the summer, you see a nice, swamp with stumps out in it. It's weird. So it's the snow melt, and it fills it, and then it's gone. So this is going to change. This pressure head is going to change throughout the year, so we should model it as a capacitor, because this head will change. So let's do that. And then also the flow that's coming in, we just mentioned it in passing, but this is going to come from the runoff from snow melt, for instance, and fill the reservoir. But that's going to change too. So the melting happens differently all the time. So we'll call that QS. That's just going to be some flow source. We won't model like the actual like snowpack and all that. We could try to bring that into a dynamic model, but we're going to leave that aside for now. Say we know how much flow is going to come out of the mountains, or we want to simulate based on different types of snowpack what the flow rate would look like and what our generation would look like. So let's start drawing a linear graph of this. So we've got a couple elements we've identified already. Maybe not quite that big. So we've got a fluid capacitor, C1. That's going to be the big fluid capacitor of the reservoir. And we also have this flow source that's feeding it, right? QS. So QS is going to flow in. And at that point, we get down to this intake. And so the intake is going to want to be filtering out debris and whatnot. So most likely it's going to be a sort of grate and potentially some screen if they need to, depending on, you don't want debris to come into your turbine. So it's at least got to filter out a pretty decent amount of stuff. So it's going to create a fluid resistance, right? It's not going to be able to push water through there as easily as if you didn't have it at all, right? So let's model that as a resistance. Call it R1. And this penstock is effectively a pipe, right? It's going to be a long, I mean, it might not be shaped like a pipe, but it's going to be a long chamber that is going to be flowing fluid through it. And surely there will be, when you have anything that fluid flows through, you're going to have some sort of resistance associated with it. But since we already just had a resistance in series here with that pipe, let's just lump that in there. So this can be the resistance for both the intake and for the penstock. We could just have another one, R2, if we wanted, but I think it's a little bit, it's nice to lump them in.
You said they're in series?
They would be in series, yeah, because it goes through the intake and then it goes through the penstock, right? So the flow wouldn't split. You wouldn't have a split in the flow. The flow rate that each one would see would be the same. So then we've got this penstock. There are other aspects of this penstock. So the first one, if we are thinking of it as being like a pipe, is that there's going to be a lot of fluid moving in one direction, right? Potentially this is a long, thin, relatively long, relatively thin penstock, and so potentially we have some inertance associated with it, right? Some fluid inductance. So I'll put that element in, and then just to be confusing, instead of using I, I'll use L1. For it's the fluid inertance is often used with the symbol I, but since it's and it's an inductance. It's a generalized inductance, I guess you could say. We often will also use L for it, so it kind of switch back and forth between L and I for the inertance. Hopefully that doesn't stress you out. Okay, good. So we have L1, and then we've got this penstock has a pressure head that helps drive. It further. There's more head down to the turbine level, right? There's this as well. So let's model that as being, it's a fixed height, right? That height, that drop from this opening of the penstock to the turbine blades is not going to change. So we can model it as being a pressure source, call it PS1. That's always going to be fixed. Now, you might say, well, why didn't we just do that with the reservoir head? We could have done that, we could have called that PS0. And the reason is that height can change, right? We want to be able to consider the possibility of the reservoir height changing. And so we don't want, we want to include the reservoir height as one of the variables that we can solve for dynamically, like based on a given flow rate of melt or something like that, what the height would be. So there's a pressure source there, and it's going to be in line, right? One side of the pressure source is going to be connected to the end here, and the other side is going to be connected here where it goes into the turbine. So the question is going to be, which direction is this arrow going to point? So PS1. The pressure at the turbine side of the penstock is going to be higher and the pressure up here, right? So this should point that direction because it's going to drop from the higher to the lower pressure. Yes?
So why isn't the resistance, inductance, and pressure all in parallel instead of in series if it's one component?
Right. So it's tricky. Sometimes it's hard to interpret which they should be. So and we had this come up with a pipe as well. So should the resistance and the inductance be in parallel or should they be in series? And I think that the most intuitive answer to that question is that the element's going to respond primarily to, so especially these inductance, but the elements are going to be responding to the amount of flow rate through the element, and this series connection allows them all to share the same flow rate. So R1, L1, and the pressure will all flow the same flow rate through them. Whereas if they were in parallel, they would all flow different amounts, which doesn't seem very physical. Like we wouldn't really think of the flow as splitting as it goes through. So that's why I think it makes the most sense to do them in series. There are other ways you could interpret that as well.
Well, logically, it just seems like they should be in parallel considering it's one component and doing all three of these things.
Right.
The way you put it makes.
Yeah. So what does happen though is that these intermediate nodes, they're like nonsensical nodes. We wouldn't think of like what is the pressure here. It doesn't really make a lot of sense. The pressure drop across R1 and the pressure drop across L1 taken separately isn't really something that is relevant. So we can mix these around in any order, and the intermediate nodes are not really of interest. Yeah. Great. And then we're going to go through the turbine, right? So we've got this interaction with the turbine that happens, and that's going to be this interface between the fluid system and the mechanical system, right? So the turbine, we're going to expand in the next lecture actually on how the turbine, what the turbine equations are, but it's clearly going to be a transducer of some sort that goes from fluid variables, so pressure and flow rate, to mechanical variables, so angular velocity and torque. So those are the variables that are going to be related through the turbine, but we're going to just focus on the high level now that it's going to be a transducer. We'll figure out the details of it in the next lecture when we actually write the equations out for this. But we have some sort of a transducer here, whether that be a transformer or a gyrator. And then we've got the rest of, so we'll talk about the mechanical aspect in a second, but let's focus on the rest of the fluid system for now. So you've got this pressure drop across the turbine, so whatever height you want to approximate that to be on the other side of the turbine, and that height is going to be go down to, it looks like there's going to be some drop, some head that'll be between that height and the outlet height. And so that's going to create another head. So we'll call that PS2, and that'll also be a constant as well. So it's also the last gaming console I've had. Thank you. Appreciate that. It was great. And so we also have to think about which direction this arrow is going to go. The pressure is once again going to be higher down here, and so it's going to drop that direction. That arrow is not super clear. That direction. And then we've got It's hard to say. This might be long enough. We don't have dimensions here, but this doesn't look like it's super long and that the fluid's all flowing in the same direction. So maybe we'll ignore the inertance here. Say there's going to be some resistance associated with going around this curve and then this outlet. So there'll be some resistance, R2. And finally, we're going to go to the river. The river's got some height, and so it pushes back with some pressure head, right, of its own. So we'll call this C2 head, the river's head. So C2. Back to atmosphere, right? Because up here, we're at atmosphere again. We started way up here at atmosphere. And we got back to atmosphere. Great. So now, let's move on to the mechanical side. This transducer, let's call this side of it 1, that side of it 2. Then on the mechanical side, so this is the turbine, so I could say turbine there. On the mechanical side, we've got this, this turbine's going to spin. It's going to be connected to a shaft. Let's assume that the shaft is not super long and thin. Let's assume that the shaft is relatively short and stout, and so that it doesn't have a lot of flex to it. Okay, so the entire shaft, turbine, shaft, and the rotor of the generator will all spin at the same speed. So they'll only really need one node, this mechanical system. And the variables that we're going to need to add here to give it some realism, first we need a nice reference here. So this is going to be angular velocity of 0. Let's say. It's a good reference. And let's also include, there's going to be the rotor inertia. That'll be a very significant effect typically. And another significant effect, probably with a big machine like this, is going to be the damping, the bearing damping, and then also the internal generator bearing damping, or bearings damping. So we'll lump that all into B. And then finally, we're going to interact through the coils with the electrical system, right? So 3, let's see if I can size that well. There we go. The element 3 is going to interact with element 4, which is going to be the electrical side. And a generator we've actually looked at before, and generators have generators are actually transformers, right? So we know that. This is going to be voltage equal to 0 over here. And we'll typically consider this side to have some electrical resistance, so R3, and some coil, some winding inductance, so L2. And then, where are you going to go with this? So the micro hydro is typically going to go into a battery, right? It's DC, and you're typically going to charge some kind of battery or some big bank of capacitors if you're feeling dangerous. And so you can model this as being, first of all, a capacitor, C3, but there will always be leakage, especially if it's a real battery, right? It's going to have leakage. I mean, even if it's not a real battery, it'll have some sort of leakage. So it's going to have some of that, and we'll model that with another resistor, R4, which is hopefully a very high resistance that doesn't leak out much. Otherwise, you're just going to be generating and losing all of it. But R4 is there for some realism. Like, okay, this battery is going to dissipate some. Maybe it's dissipating some to a load. Maybe R4 could be used to apply a load to this. Or maybe it's just being stored, but the R4 is going to dissipate a little bit over time. Which is why batteries, like I don't know if you guys have ever, the ones that you guys buy, like Duracell batteries or whatever, AAAs, AAs, those things are pretty shelf stable. They don't leak too quickly, but they do. But if you, especially things that are rechargeable, those things leak quick. So if you got something that's rechargeable and you charge it up and a month later you come back to it, it's like completely dead, even though it wasn't on. You gotta recharge it. So that's kind of what R4 is there for. Unless we actually use R4 to be some sort of load that we're driving like a heater with it or something. That'd be a good thing if you're a prepper, you drive a heater. Okay, this isn't about preppers. This lecture, it's not. I promise. I've actually exhausted all of my understanding. They also get seeds. And I occasionally get Christmas presents from them too. It's like I've got like a flashlight, a flashlight radio that has a hand crank to charge it up. Yeah, that's pretty cool actually. I like that one. It's fun to just do. It just sounds fun. And then I've also gotten a tin of seeds. Like beans and corn and so we can rebuild. We can rebuild. And I'm not saying that that's bad. I think that's kind of cool, but also like I hope it has instructions because I don't know what I'm doing with those seeds. I would be like, I need to Google how do I plant these seeds, and it'd be like, oh, I get it. That sucks. Yeah, this Wi-Fi sucks. But I'll at least be able to charge my iPhone, so that'll be good. There won't be any internet, but all right.